Hello, my name is Paul Bemis. I am the president and CEO of Applied Math Modeling, and I'm going to talk to you today about improving energy efficiency in the data center. First of all, Applied Math Modeling is responsible for the sales and support of the CoolSim data center modeling application. CoolSim has been around since about 2008 or a little bit prior, and it is primarily focused on cost-effective simulation for data center analysis using a software as a service model of delivery. We are experts in the field of CFD, sales, development, and support. Have been doing this for about 20 years. We also provide consulting services for data center design and for building science professionals. Oftentimes, it is not a data center, it's a laboratory or an indoor water park or other applications, and we can model those as well. CoolSim, however, is focused primarily on data centers, but more and more can be used for other things as well, indoor airflows related. So let's talk about data centers. This is what the inside of a data center looks like for those of you who may not have ever visited one. It is just a big, long row after row of equipment. We're looking primarily at the inlet side here. This is probably a cold aisle, although it could be a hot aisle. It might have a ceiling on it, but they're arranged in a way where the air blows. If I assume hot here, it blows to the inside on both of these and then down and up out of the ceiling. Data centers are essentially racks and racks and racks of high-density IT equipment. From the outside, they look kind of boring. They're just a big building. There's not a lot of cars in the parking lot because it doesn't take a lot of people to run these things, relatively speaking. It is an issue of maintenance and replacing equipment periodically. But you see here on top of the buildings, these are heat exchangers. They are dumping a bunch of heat out into the atmosphere. Here we have diesel generators that run in the case that you have a major grid outage. The diesel, they're generally diesel generators, will fire and run. Here again, these are heat exchangers. These are chillers. They're dumping heat to the atmosphere, as are these. And then you have the diesel generators typically here that power it in the case of a grid outage. Water consumption on these data centers can range quite a bit depending on what kind of cooling they use. If they use evaporative cooling, they can be quite hungry with respect to water because they're using it in an evaporative sense to cool their systems. If, however, they're using it with dry coolers, what we call dry coolers, then it is quite a bit less. So water consumption is a function of how they are designed. Power consumption is somewhat of a wild card in terms of the prediction. We all know that power consumption for data centers is rising quite dramatically, and you see here quite a variation over time as to how much. This is the upper end. This is the worst case condition, generally, of power increase over time. Here we have something more like expected, but still what you're seeing is we're getting near 1,000 terawatt hours of capacity for data centers. This is going to continue. The use of artificial intelligence has driven this tremendously. So no matter what source you look at, you'll find data centers are becoming a larger and larger percentage of total electricity generated in the world today. It used to be that it was in the range of 1.5 to 3%. Now I hear reports that it is higher than that, upwards of 5 to 10% of all power generated goes to power data centers. And remember, every one of our phones and every one of the devices that we use, including the one I'm presenting to you today on, goes through a data center. So they will continue to grow. There's no question about it. In terms of where it stands with respect to others in the industry, heavy industry is the biggest consumer, electric transport, space and heating and cooling. This is for buildings, and then data centers. So it's in that top 4 or 5 expected growth range entities. So let's talk about energy effectiveness. The popular metric that is used by many is power utilization effectiveness, PUE. PUE is a ratio of the total energy consumed by the entire facility divided by the IT energy itself. So if all you had to do is power the servers, then you'd be in fairly good shape. But you also must cool the servers, and that comes into the numerator. And this ratio was intended to supply an indication of how effective the facility is delivering cooling to the IT equipment. So let's look at total facility power first. It is made up of all this stuff. Chillers, water pumps, towers, condensers, UPSs, transformers, everything that consumes energy, plus the IT equipment itself. So if you were able to eliminate all of this stuff here on the left, your PUE would be 1 because it would just be IT energy over IT energy. But you have to cool it. Unless you're going to run your servers outside, which is impractical, you have to cool it and you have to power it with UPSs and so forth. But if you look at all that stuff on the left as a percentage of total load, non-IT load in this case, we find that 75% of all of that energy predominantly goes to cooling. Everything else is second order. So it's really, if you look at this chart, you see it is the chiller, it is the crack unit itself with the fans in it that dominates the total situation compared to the IT equipment over here. The IT equipment being 33%. It is dominated by chiller, cooler, fans. So really the equation becomes cooling power in the numerator plus IT energy. That's really the best way to look at it. That is the dominant parameter, is cooling power. If you concentrate on reducing your cooling power, your PUE will come down. The rest of that stuff all gets reduced over time because the equipment is becoming more efficient. So you can ride efficiency curves by buying new equipment that is more efficient. I'm talking here about transformers and power distribution units and IT equipment itself. But it is the cooling power that you must concentrate on. Focusing on cooling efficiency will provide the biggest payback to a data center, and understanding how cooling systems work is key to this entire process. So let's talk about data center cooling power. Total cooling power in a data center is the result of the fans that are on the cooling unit itself, the chiller, fan power, plus the cooling load. The cooling load is what's in the room. So what is in the room is the load, the IT equipment and everything else that generates heat, including people, divided by the efficiency. The coefficient of performance is the efficiency at which you can pump that load outside, outdoors, out somewhere. And the total cooling load itself here in the numerator that I was just referring to ends up being the racks. Remember, all power that goes into that room turns into heat. PDUs turn into heat, UPSs, and fan power. Do you remember that law of thermodynamics says if you put energy in a room, it's going to ultimately turn into thermal. Doesn't matter. An adiabatic closed room with a fan in it will get hot. So fans are something that are there. The fans you actually pay for twice, once to power them and then once to reject their heat out of the room. So total cooling power really becomes the fan power to get the cooling air into the room, plus racks, PDUs, UPSs, and the necessary energy to get the heat from those fans back out, divided by the efficiency of your heat rejection system. This is the total cooling power. So that's how you look at it. Remember that cooling units are really heat pumps. That's what they are. They're pumping the heat outside. A heat pump uses shaft power to provide the movement of energy from one location inside to another location outside. It's a pump. It pumps heat. And the coefficient of performance of the heat pump is the ratio of the heat moved compared to the work supplied. The work supplied is generally shaft power. They're turning a crank, they're turning a shaft, generally to compress a medium such as refrigerant so that it gets hot, hotter than atmosphere, so they can then transfer the heat to the outside and then expand the gas again to drop the temperature and run it back through the system. So the coefficient of performance is a ratio of the amount of heat that can be dumped divided by the work required to dump it. So that's the thermal load in the room, including the fans, is in the numerator, and in the bottom is the energy required to cool it. Generally drive the chiller, that's what you're thinking, or compressor, whatever it happens to be, to cool it. That's the ratio. You can do this for the entire data center. You can develop a COP for the data center that is a ratio of these two things. That's something ASHRAE is working on. It's called the mechanical load component. And it is something that's becoming a popular along with PUE. Now, let me remind you that fan power, by the way, is a cubic relationship. That the differential in power to a fan is cubed in terms of energy consumption. So if you decrease the flow by just 20%, it's going to reduce the horsepower by 50% because the relationship is cubic. This is true for pumps, this is true for fans. So if you want to reduce your energy consumption, slow your fans down. It's actually often more efficient to slow them down than to shut off one or two and leave the others at full speed. Depending on the situation, just slowing them all down will make a bigger difference with respect to energy savings than it would be if you were to shut one off. So, steps to optimize cooling efficiency in a data center and reduce operating cost. First, determine the total amount of airflow required to satisfy the IT thermal load. I use a rule of thumb, this is the American units, so I tend to use 100 CFM per kW. It's a little bit, conservative. I mean, you should really use 125, I suppose. We used to use 156, but the math is harder when you use those numbers. So 100 is a good number to keep in mind. Rule of thumb, 100 CFM per kW, that assumes about a 30-degree temperature rise across the servers, and that's fairly good for new equipment. New IT equipment can handle a higher delta than the older stuff. So what you do is strive to reduce the supply airflow to match what that IT load looks like. So take the total load that's going into your data center, you can read that off the UPSs, or you may know what you're designing for with respect to that room, multiply it times 100, and that is your supply requirement. Now you need to try to only supply what is necessary and not more. That has two key benefits. One is it reduces the fan power required. Remember, that's cubic, so that's important. And number two, it maximizes that return air temperature, which makes the heat rejection system just work that much better. And then, once you've done that, begin to increase the supply air temp until it gets to about 77 degrees on the supply side. At 77, the ASHRAE spec in Fahrenheit is actually 80.6. That's the recommended inlet temperature for servers, but what happens is you get up around 77 and the IT servers start to ramp up. They have variable speed fans. They'll start to ramp up and therefore you're using more energy. So generally speaking, I encourage people to run their data centers with supplier temps around 70, 75. Don't really go much higher than 77. And then use containment to keep the hot and the cold from coming in contact with one another. And that unifies the rack inlet temperatures pretty well. So a little bit about air management. We are seeing a lot of liquid cooling as well, but air will always be there. Remember that even in the case of liquid cooling, you're only cooling part of the system. You're not cooling at all. And liquid cooling is not perfect. There'll always be a requirement for air. So let's talk a little bit about it. There are two terms I would like to make you aware of. One is just recirculation. In this case, there's not enough cooled air coming to the rack, so it's going to recirculate back around on itself because it needs to get air into that intake and it's going to pull it from wherever it can. If there's not enough cold air supplied to the system, it'll recirculate on itself, particularly if it's not contained. Bypass airflow is the opposite problem, when you're supplying too much air and it's blowing by and actually cooling off the exhaust. That's bad because it tends to drive up the return air temperatures. Turn down the return air temperatures, make them worse. So the delta T across the cooling units is not sufficiently high enough to be able to give it good cooling capacity. So you want to eliminate bypass, and you want to try to reduce recirculation as much as you possibly can. Reducing them, making them optimal, is how you get to the lowest energy point in a data center. So let's take an example. This is an old IBM data center here, and I have this in 3D so we can take a look at it. It's sometimes helpful to look at it in 3D. It actually tells you more. And here what I'm going to show you is some of the results from this data center. These are some CoolSim results. Before I go there, let me just go over this a little bit so you know what we're looking at. These are the racks along here. You see the little red means that there are cable cutouts underneath them. There are holes in the floor. This is a raised floor design. It is a perimeter cooled design. It does not have any containment. So the air is being circulated in the room. It's being mixed. This is very characteristic of early designs that we saw. The racks are lined up correctly. Hot aisle, cold aisle, that's not so much of a problem. You see airflow indicator suggests that this is the cold aisle. And this is the hot aisle over here, and so it alternates as it goes across. But we have this funky situation where we've got some racks perpendicular here. We also have gaps between these racks. We also have underfloor cable trays that you can see here. And the depth of the floor is not as great as you might like it to be. So in CoolSim, you can now model that quite effectively. Let's first take a look at the data center energy report. You notice the RTI, this is a Department of Energy parameter. RTI is 100. That means that it's supplying exactly enough air to meet the demands of the racks and no more. So if we look up here, we can see that the supply airflow is actually 115,212. The demand is 115,350. So they're just about spot on. That's perfect. You can see here that it's at 100. But you can also see that we're seeing some hot spots here. RCI, which is the rack index, the rack cooling index, is 89. That's getting into the red zone. That's a problem. We don't have any problems with hot spots. This is the low end of the range. This is below ASHRAE spec. But we've got some issues with hot spots in the room. Let's go have a look at where they are and why. So over here in the CoolSim report is the 3D output. One of the ones I always go to first is the recommended inlet temp range. And you can see here that I'm out of range. This is a compliance plot, so I'm looking at temperature. This is the ASHRAE range of recommended temperature, inlet temperature on the racks, which is how these are defined in terms of specification. 64.4 is the low end in Fahrenheit, 80.6 the high end. You can see I've got some problems here. Over here I'm out of range, I'm hot. This is very classical of an environment like this that is mixed, even though I've got the perfect amount of air coming into it, and I'm within ASHRAE range, so I'm up in the area I should be for supply temp. We've got problems. We've got problems with hotspots. So the question becomes why? One of the answers to that is that you do not always get uniform distribution of air in the room on the perforated tiles. And the reason for that is pressure variation in the floor. So if we take a look at this plot and I flip it around so you can see it and I turn off perspective, this is a plot of tile performance. We're looking at airflow out of the floor tiles as a function of color. You can see I've got a variation in the floor tile performance of almost a factor of 2. You can see it's highest in the middle because this is a perimeter system. These are the cooling units around the perimeter in blue. They're blowing air to the center, and my highest performing tiles, therefore, are at the center. This is because the static pressure is highest in the center. Remember, total pressure is a combination of static pressure plus dynamic pressure. So as the velocity slows down, the static pressure rises, and therefore you get best performance out of the tiles in the center of a room like this. You get worse performance when they're near a cooling unit because the underflow velocity is so high there's no static pressure. I have been in situations where these tiles will actually pull air out of the room down into the floor instead of blowing it out, because the horizontal velocities under the floor are so high that it pulls. It creates a low pressure underneath that floor compared to the room. You can see this visually in some of the path line plots we have. This one's kind of fun. This is path lines from tiles. So let's go look at the path lines coming out of the tiles in this section of the room that's performing so badly. In CoolSim, you can hide these surfaces. This is an ANSYS feature or an ANSYS partner. And you can see here the path lines are bent coming out of that underfloor because the velocities under this floor are so high that it's just trying to race by. And even when it finally gets to come out, it comes out at an angle. So this upper region is no longer getting cool air. And as a result, it begins to pull air from its own returns. Over here, we've got the opposite problem. We've got bypass airflow over here, where the cold air should come up and just enter the rack. If it were perfect, it wouldn't go anywhere. You'd just see it coming up and stopping. But you see it's coming up and going over to the cooling unit. Well, that's a problem. That's bypass airflow, because what's happening here is it's going up and over the top and cooling off the returns of these heat exchangers. And that's bad, because the delta T drops on these and their cooling capacity will actually decline. You can see these are colored by temperature, so you can see they're cold in the beginning down at 65 degrees, but as they get over to that cooling unit, they warm up into the 80s because they're mixing with the hot air coming out of the back of these units, and that's bad. I'm oversupplying in some areas and I'm undersupplying in other areas within the same data center. And that's generally the problem you'll find in these kinds of designs. Here's another shot here. This is of the path lines of hot, where we show them separately for clarity so that you can actually see what's going on. So here's the hot side. You see it going back, but we have some recirculation. Look what happens. We have rack recirculation going on right here. So it's going around the end, and it's going around the end cap because this tile is performing poorly because it is too close to this unit. Same thing over here where we were looking before. Let me go over to this section. And over here what you see is it's coming over the top. It just gets sucked right over the top into the intake. So that's a very clear case of rack recirculation being caused by inadequate air to the IT server. The irony here is we've already shown you that we have exactly the right amount of air for the room. The problem is the air is not going to the right place in some cases, and in other cases is too much air. So regulation of the air has always been a problem in data centers that have no containment. There's no hot aisle or cold aisle containment. Containment is a way really to build a box around the hot aisle and force it back to the return units, or to box in the cold aisle so that it doesn't mix with the hot aisle. So that's an example data center. Here's another one. This is a newer design. This is what we call basically a hyperscale design. These are fan walls. These units are delivering air. There's no raised floor here. They're sitting up in the room. They're large so that you get a lot of mass flow out of them without a lot of velocity. The servers sit in the middle. This is a much better way. This is hot aisle contained. So you see here this black box is around the hot side. The air is being blown from front here to back. Those are arrows, and you see it being pushed into the hot aisle. So it comes out of the fan wall and into the room. These are just diffusers to try to unify the flow a bit and slow it down. They come into the room, go into the servers, go into the hot, come up through the ceiling, back around, and make a circle. So in these designs, you have this situation where the air recirculates in a pattern that looks like this. Now let's go look at this one. This one as well, let's first take a look. You can see here that we are a little bit light on supply. This number should always be 100 or less. We're a little bit light on supply airflow, which is going to cause some problems. It's creating a few hotspots in the data center. Again, these are from Department of Energy DCEP training. If any of you have taken the Data Center Energy Practitioner training, if you haven't, I would recommend you do that. And here as well, analytically, you can see, or numerically, that we're supplying 752,000 CFM. The racks need 772, so we are a little light. This is going to show itself in rack inlet temperatures you see, and of course in the center is where you have some issues. Always in the center in these designs, because by the time you get to the center, the air is leaked by some of the servers, you don't have enough, and so you fall out of specification in the center. Same plots of supply air and return. We might be able to see, if we take a look here, some of the recirculation happening on the back of those servers. They are going to recirculate on themselves a little bit. Might be hard to see here because of so much going on. You see the hot going into the returns there, into the hot aisle and up through the ceiling and back to the cooling units. So that's how the flow occurs. On the cold side, you'll see it coming in and supplying the room with cold air. So here's the supply side. Notice much of it is going to the servers in the edges, but not a lot is left by the time it gets to the middle. That's because of leakage that occurs between the racks up against the containment. All data centers leak. The question simply becomes how much. And here, if I take a slice of, let's see, Y, 74 inches in Y, we're taking a temperature slice here. This is all part of the CoolSim output. And let me flip it around into the Y direction so you can have a look and normalize it. Take off perspective so we can see. And we can see this is a thermal map. We're looking at temperature here, and we see temperature leaking out of the hot aisle into the cold aisle because we have pressure differential that is not positive from cold to hot, caused by not enough supply air. So we would look at this from a pressure point of view. We would find that the pressure differential is backwards. And here it's higher in the center, and it is lower outside here. And that's causing it to run backwards. This is a very typical situation that we run into with some designs. I highlighted it here so you could see it. I kind of manufactured this when I ran the supply air just a little low so that you can see the effect of leakage. All systems do leak. All containment does leak. We can look at it from a variety of points of view, including animation sequences, but suffice to say that that is the problem with these kinds of designs. Now, in terms of trends, what we see is, again, sensitivity to carbon reduction, renewable integration, renewable energy is something that I think we're going to see a lot of with data centers, mostly because we need it quickly, and it is the quickest way to deploy power in the world today. We're going to see load modulation and scheduling. I'm seeing incentives being discussed where they ask data centers to curtail their consumption of power during peak periods and provide economic incentives to do that. We are seeing liquid being added, both direct to chip and rear door heat exchanger, as well as immersion, which I see less of. These first two are quite popular. This will reduce most of, up to 80% of the thermal load in the room, but not all of it. There'll always need to be some air cooling and analysis of airflow in a room, because things like power supplies and memories and UPSs are all still going to be air-cooled, and you'll need to handle those. We're also finding, infrastructure that's got NVIDIA chips already deployed on it, and oftentimes direct-to-chip liquid already included in the design. And we'll see more automation and artificial intelligence and, of course, machine learning to understand how to best optimize energy efficiency in these data centers. So it's going to continue to grow. We're going to see bigger data centers with higher power densities. The focus on energy efficiency will continue to be an important topic, as will resiliency. No one likes to not be able to use their credit card or debit card at the gas pump. Resiliency is going to continue to be a big deal, particularly as it relates to climate change. Renewable energy, I believe, is going to become a key to meeting a lot of these demand growth issues in data center design, primarily because it's the quickest, lowest cost way to deploy energy. And I believe noise is going to continue to become more and more important because these things are loud. Inside the data center, you hear fans. Outside the data center, you hear fans and compressors running, and often diesel generators in certain situations running as well. Sound and living near these Sound will be an issue, and living near these data centers will be problematic for those who are adjacent to them. So that's a quick summary. Again, applied math modeling, CoolSim software. You can find us on the web, and let us know if you are interested in discussing any of these issues in more detail, if you would like to use our software, or contract us to perform modeling services on your behalf. Thank you, and have a good day.